Alright guys, welcome back. We're going to keep talking about water, and if we're talking water, one of the things we really can't not talk about are mixtures, because when we talk water, it is rare to find water in and of itself hanging out on Earth. It's often part of a mixture, and a mixture is simply the combination of two or more substances that are not chemically united, but they sort of share the same space. Alright, so if we remember all the way back to when we started talking some of our review of basic chemistry, we talked about the difference between a pure substance and a mixture. So pure substances include things like your elements and your compounds, where no matter where I take it from anywhere in the universe, that element or that compound is going to retain those properties. If it's a compound, it's going to be found in the same proportions, it's going to act the same way. Mixtures, on the other hand, don't really follow that process. In fact, I can take a mixture of sand, for example, even a couple of inches from each other, and the substances that make that up in terms of proportions may be slightly different from one another. So when we classify mixtures, we talk about them being either homogeneous or heterogeneous based on how the substances that come together in that mixture sort of share their space. So a homogeneous mixture, I'm looking at something that's got a uniform composition throughout its mixture, uniform appearance. We often refer to these as solutions. So if you look at a solution of salt water or mouthwash or black coffee, it's really hard for you to look directly at it and be able to pick apart the pieces because they're so uniformly spread out throughout that substance. Heterogeneous mixtures, however, or what you may have come across as suspensions in the past, these often are much easier to pick out the different components, figure out where they are at any particular point in time. So sand, if you were to look closely, or even do it under a microscope, you could see the different colors, the minerals and rock that make up that sand. Oil and water, or think of salad dressings, a great example of heterogeneous mixtures, right? Especially something like Italian dressing, you can pick out the different herbs, you can see if you let it sit long enough, the oil and the vinegar separate, so on and so forth, so you can see those different particles. We're going to focus mostly on the solutions because when we talk water, water is sort of the quintessential solution maker. So a solution in and of itself, right, uniform mixture of two or more substances, it is a homogeneous mixture. And when we talk solutions, we've got two basic components or two basic parts to any solution, your solvent and your solute. And your solvent is the substance that's actually doing the dissolving, and typically is present in a higher concentration or a larger amount, as opposed to the solute, which is what is actually getting dissolved. So let's talk something like salt water, and water is your solvent. It's the material that salt, which is your solute, is getting dissolved into. Other examples, Kool-Aid, right? So water, once again, is your solvent. It's doing the dissolving of the Kool-Aid, which is your sugar and dye and flavoring that's in those packets. Okay, and both of those happen to be specific examples of aqueous solutions, where water acts as the solvent. And we often talk about water sort of being this universal solvent. It dissolves a lot of different things, and rarely do we find water in nature not part of some sort of solution where it's acting as a solvent dissolving something else. So if water is in fact this universal solvent, then what does it dissolve and how does it work? So I'm going to throw a statement out there in a couple of slides, but I'll bring it up now. This idea of like dissolves like. So while water is a universal solvent, we know water doesn't dissolve everything. You stick water and oil together and they're not going to mix, they're not going to dissolve. But water's really good at dissolving a lot of different things. So while it doesn't dissolve everything, it dissolves a lot. And once again, this gets tied back to the fact that water has those slightly positive and negative regions of the molecule because it's a polar covalent bond that's holding those hydrogens to the oxygen. So water is able to dissolve anything that is like it in the sense that it can dissolve anything else that also has some sort of charge associated with it. So one of the things that water is really good at dissolving are ions or ionic compounds. So something like sodium chloride, for example. So the ions in the sodium chloride come apart as water smashes into that salt crystal and yanks off individual sodium ions and individual chlorine ions, and you get dissolving happening like what's going on here in the picture. So water's going to brush up against this either because it's just going to naturally happen because it's sitting there, or because you're heating it up and you're forcing these molecules to move faster, or you're stirring them and they're going to hit. And what ends up happening is that those individual chlorines and sodiums pop off of that original salt crystal and they get surrounded by the water molecules because those molecules are attracted to the positive and negative ions. And in fact, if you pay really close attention here, and this is a really good thing to take note of, take a look at how that water ends up arranging itself around those different ions. Do you notice that it's different? Your chlorine ion is negative, right? And so opposites attract, even in this case. So you get those hydrogens which have those partial positive charges. That's what's going to be surrounding that negative chlorine, right? Positive and negative attract. The opposite happens to the sodium. Now I've got my slight negative charges from the oxygen, and that's what surrounds the positive sodium. Positive and negative attract. And so you end up with what we call hydration shields. That's what's going on here. And that hydration shield simply means that each of those individual ions, as they get yanked off that original salt crystal, get surrounded by water, and as a result, so long as that water is in place, that water is going to surround each individual ion and prevent those sodium and chloride ions from coming back together. Now, if you leave the water sit on the counter long enough, say a couple days, maybe a week or so, and that water starts to just naturally evaporate at room temperature, as those water molecules disappear, what do you get left behind at the bottom of the plate? But salt. Why? Because you're removing those hydration shields, and that sodium and chloride can come back together and reform the salt crystals. Now, water can dissolve anything that's ionic because of those ions having those charges. But compounds don't have to be ionic to also get dissolved by water if they themselves have partial charges to them. Something like sugar, for example, we also know gets dissolved. Why? Because it's polar. Alright, and anything polar means it's like water, which is also polar, and so they have those positive and negative charges, partial positives, partial negatives, to also get attracted to those water molecules. And something very similar is going to happen here, but rather than it being individual ions that get separated, they're individual whole sugar molecules that get separated and shielded from each other. Something else we can talk about with solutions. So water can dissolve anything like itself, right? Anything polar, anything ionic. But regardless of what kind of solution we're talking about, there's only so much you're going to be able to dissolve within a particular solvent because of this idea of solubility. So when we create solutions, solubility is talking about the maximum amount of a solute that can dissolve in a given amount of solvent at a consistent temperature or constant temperature. So there's really three parts that we need to consider when we talk about the solubility of any solution. What's the solvent? How much of the solvent do you have? What's the solute? And then what's the temperature that this is happening at? You change any one of those parameters, the solvent, the solute, how much of the solvent or the temperature you're doing at, and you will end up changing the solubility of that solution. So think about it. If I've got a solution sitting at 20 degrees Celsius and I have 100 grams of water, I can only add at that temperature, in that volume, of that solvent, of this solute, 203.9 grams of table sugar. That's its max. And that's what we talk about as a saturated solution. I have dissolved as much of my particular solute in that given amount of that solvent at that particular temperature. If I increase the amount of solvent that I use, I'm going to increase how much sugar I can dissolve. If I increase the temperature, I'm going to increase the amount of sugar I can dissolve. If any of you have ever heated up water on a stove and tried to dissolve sugar, you're going to get a lot more sugar to dissolve there than you would if you left it at room temperature. If any of you have hummingbird feeders, that's a quick, easy way to make hummingbird food without having to buy it. Alright, but you need to heat it up because you need to dissolve more sugar in that solution than you would be able to do in that same amount of water at room temperature. They like lots and lots of sugar. And if I were to change the solvent, that would also change how much sugar dissolves, or if I change the solute, it's going to change the volume. So any of those parameters that we change will end up changing that saturation point. But the point here is the saturation, or a saturated solution, is holding as much as it possibly can. If I try to dissolve 204 grams of table sugar at 20 degrees Celsius in 100 grams of water, that last tenth of a gram of sugar is not going to dissolve. It's going to sit at the bottom of your beaker, and no matter what you do, no matter how much you try to dissolve it, it's not going to dissolve unless you change another parameter. Now, if you only dissolve 203 grams of table sugar, then you're talking about an unsaturated solution, in which case you're now 9/10 of a gram less than the max that water can hold at that temperature. So unsaturated simply means it's got less than the maximum amount of solute, given the temperature, given the solute, given the solvent, and the volume of the solvent that you're currently working with. So here's that particular statement I want you to keep it in the back of your head. Say it over and over and over again to yourself. How do you know how quickly or how easily a particular solvent will dissolve a solute? Well, if you understand that like dissolves like, and you understand the chemical properties of the solvent and solute you're trying to put together, you should be able to determine whether or not those two things will readily mix together. So our concept, or our topic here right now, is water. So we're dealing with things that are readily going to dissolve in water or are not. And so there's two terms that we can utilize to describe how easily something dissolves in water, and those two words are hydrophilic versus hydrophobic. So anything that readily or easily dissolves in water is something that's hydrophilic. So they easily dissolve, which means they're like the water in terms of their chemical properties. So when we talk hydrophilic substances, these are things that are either ionic, because they've got those charges, or they're polar, and so they've got those partial charges. Either way, those charges exist in that solute, which means they get to interact with the partial charges in water as a solvent. On the opposite side of that, anything that's hydrophobic is nonpolar. It's not like water in the sense that it does not have any partial or full charges to interact with those charges that are going on in the water, and so they simply don't dissolve in each other. Something like oil or fat, those are hydrophobic substances. They're nonpolar, they don't have any charge, and so they won't end up dissolving in water. We can also talk about these interesting molecules that exist called amphipathic molecules, and these tend to be big molecules, but they're interesting in the sense that they have regions of the molecule that are hydrophilic, and so regions of the molecule that will readily dissolve with water and interact with water. But they've also got regions that are hydrophobic that don't. Soaps, detergents, or what we call them collectively as surfactants, they are amphipathic molecules. They have a polar end, which ends up getting attracted to water, but they also have a nonpolar end that gets attracted to things like dirt and oils. And that's what makes them such great molecules to clean things with. So if I take a look, here's a general soap molecule. Here is this large, long hydrocarbon chain. Nonpolar chain doesn't have any charge to it, and so this is the region that ends up attracted to other nonpolar things like my dirt molecule here, but will not interact with the water. Flip side to that is it also has this region, this short ionic component to it, and it's got charge. So that charge then ends up interacting with the partial charges in the water. So how does the soap work? Well, here's my sort of dirty, oily, greasy stain, say maybe on a plate that you're washing in the sink after dinner. Water molecules come in, they sort of just wash over them. Alright, so what are you going to do to get it off? Well, you're going to have to use some soap. And what that soap ends up doing is you've got those nonpolar tails that are now attracted to that dirt, so they'll interact and dissolve with each other, sort of surround and lift that dirt particle off the plate. At the same time as you're running the water over that plate to clean off the soap, you get those hydrophilic heads, alright, that are ionic. They have that partial charge. They're attracted to the water. They've now surrounded that dirt molecule, lifted it off the plate, and take it along with them as these guys get attracted to the water that's going down your drain. So they work really kind of well in the fact that they're able to dissolve those dirty, grimy, oily messes. Same deal in your clothes. Alright, you want to run your clothes through the washing machine. Alright, the only thing that's going to get that stuff out is if you've got some soap in there. Why? Because those nonpolar tails get into the fibers of your clothes, surround the dirt, and then also get attracted to the water because of those hydrophilic heads, and they get washed down the drain. In nature, we've got a particular amphipathic molecule we'll spend a lot of time talking about later this year, called your phospholipids. Alright, and phospholipids have a very similar structure to that soap molecule in the sense that they've got these long hydrocarbon chains, what we'll call fatty acid chains. They don't have any charge to them, but then they also have these phosphate groups, or these polar heads, charged heads to them. And so your phospholipids are a major component to the membrane that surrounds the outer covering of our cells. And they end up forming these bilayers, or a double layer around your cells. And there's a reason for it. You've got lots and lots of water that's going on outside your cells in your environment, and the interior of your cell, something we'll call your cytoplasm, also has a lot of water to it. So what ends up happening is that these phospholipids form this double layer, and it has to be a double layer to make this work, by the way, where those heads, which have a charge to them, can interact with the water both in and outside your cells and sort of wall off or seal off this internal compartment here full of these fatty acid chains where they don't have to interact with the water. And so you get this double layer that ends up forming a barrier between the outside of your cells and the inside, and the chemical properties of these phospholipids are really going to drive what gets in and out of your cells, and we'll talk about that a little later this year when we talk about cell transport.